Cars pass by at an altitude of 625 meters, treating the surface exactly like an ordinary ground-level street. Yet, the height of the Huajiang Grand Bridge is actually its second most impressive feature. To even begin placing the first cables, construction crews had to split an entire adjacent mountain in half just to reach the site, committing hundreds of millions of dollars to tear through rock in a virtually unpopulated gorge. Raises an immediate question. What exactly is the logic driving a project of this scale? The answer reveals how national strategy is applied. When geography refuses to cooperate with long-term economic goals, the terrain is forcibly rewritten. For centuries, the province of Guizhou was defined by isolation. Over 90% of its landmass is locked entirely in steep mountains and high plateaus, acting as a massive natural fortress that kept the region disconnected from broader economic markets. Navigating this terrain exacted a heavy daily toll. Transporting basic agricultural goods or reaching a local school required a grinding, hours-long journey through near-vertical switchbacks. Localized attempts to cross the deepest valleys relied on small, fragile suspension bridges. These narrow crossings provided basic survival, but they could not handle heavy commercial traffic. In the late 1990s, planners stopped trying to adapt to the mountains. The new directive was to cut directly through them, initiating the construction of an aggressive, interconnected grid of highways and high-speed rail. This map details that exact strategy. The S57 and G56 routes operate as active economic arteries, interrupted by one glaring gap, the Huajiang Canyon. Sealing that gap was the objective. By bridging the canyon, the deep southwest is fully integrated into the macroeconomic corridor. Poverty in environments like this rarely stems from a lack of inherent resources. It is almost always a strict function of isolation. Getting the bridge built required solving a massive logistical paradox. Before assembling this structure, engineers had to figure out how to deliver materials to a vertical cliff face with zero existing access roads. The violent solution was to deploy massive drills and precisely sequenced explosives, tearing through solid rock to carve out a V-shaped access fissure. Once at the edge, a traditional bridge design was mathematically ruled out. The sheer depth of the gorge made placing a central concrete support appear entirely impossible. The only viable option was crossing the entire gap in a single bound. That required suspending a main span of 1,420 meters across a total project length of nearly 3 kilometers. To make that suspension work, the engineering had to adapt to the uneven canyon walls. The result is an asymmetrical design, relying on two distinctly uneven towers, one standing 262 meters tall, the other 205 meters. Structural engineering at this extreme scale cannot force perfect symmetry. It has to mirror the jagged reality of the mountain it sits on. That solved the design. But the next logistical nightmare was assembly. There was absolutely no solid ground below to install heavy lifting machinery. Engineers bypassed the ground entirely. They installed a high-altitude cable crane system, turning the empty sky above the canyon into the primary mechanism for flying 49,000 tons of steel directly into position. Guiding those massive steel sections required aerospace technology. The project tapped into the Beidou satellite network to provide millimeter-accurate spatial positioning from orbit. Traditional manual spotting was replaced by IoT control rooms and live digital twin models. Construction was managed entirely through real-time data streams. This cross-section demonstrates the greatest invisible threat to the completed structure, the Venturi effect. The natural shape of the gorge acts as a funnel, taking normal wind, compressing it, and violently accelerating it right as it strikes the bridge deck. To combat that constant shear force, along with potential seismic activity, The structure utilizes LiDAR Doppler for advanced wind tracking and hydraulic damping to actively absorb shocks. The bridge even has its own internal nervous system. Optical fibers are woven directly into the main suspension cables, constantly streaming real-time stress and tension data back to a central control hub. At this level of complexity, the bridge operates more like a living organism. It feels its environment, reacts to pressure, and continuously works to survive the canyon. The return on this engineering investment becomes obvious when you measure the speed of transit. Historically, navigating down the mountain and back up the other side took anywhere from 70 to 120 grueling minutes. Today, drivers cross that same expanse on a straight, frictionless path in roughly 1 to 2 minutes. That efficiency dictates reality on the ground. Commercial goods now flow without interruption. Local populations have rapid access to central healthcare facilities, and educational logistics are seamless. The structure has also evolved past pure utility. By integrating a high-altitude coffee shop, a glass-bottom viewing floor, and extreme sports facilities, it generates its own distinct revenue as a destination. By eliminating the geography of isolation, the bridge effectively compresses the timeline of regional development, directly linking rural production to macroeconomic markets. Looking at the region today, the imposing mountains that once locked populations in isolation are now effectively just scenic backdrops to human movement. In the 21st century, national power is a function of logistical speed. Connectivity defines a region's economic ceiling more decisively than the raw resources it possesses. If humans can map satellite data, weave optical fibers into steel, and literally split a mountain to turn a 2-hour struggle into a 60-second drive, then the Huajiang Bridge proves that even the most extreme terrain, from 600-meter drops to violent canyon winds, can be mastered when a nation decides to prioritize the speed of its own connection.